Hello everybody and welcome to week 2 of building scalable distributed systems. This week we're going to look at concurrency. Being able to handle concurrent behavior in a distributed system is absolutely fundamental to building scalable, available systems. And for many of you this may be a refresher, but we're just going to go over the basic problems that concurrency introduces, and then as you progress through this module, you'll be doing some reading from this very fine book, which will talk you through many of the facilities in Java that are available for building concurrent systems. But really, let's just go through some of the basics of concurrency to set you up for your reading. Concurrency is absolutely fundamental to building scalable systems. Whenever you distribute a system across multiple nodes, you're inherently getting concurrent behavior because the nodes can execute things at the same time. So events happen on different nodes at the same time, and you can't control the order of those events. So you need to have some way to coordinate all of your concurrent behavior. And you also need concurrency on nodes to be responsive, because if you can handle multiple things at the same time on your node, you can actually achieve higher throughput. So concurrency is absolutely essential, and you need concurrency at the system level across different nodes and on the actual node level, basically different threads on different cores in your system. So most systems we use now are multi-core, they have multiple CPUs, and to exploit these effectively we need concurrency. It's essential to run things on different CPUs at the same time, and also to exploit waiting time. When a thread tries to read from disk, it waits for the disk to respond with data, and there's latency. You don't want that resource, that CPU, to be waiting, doing nothing. So while one thread is reading from a disk, another thread can be executing something else, some other instructions, some other useful work. When the data returns from the disk, the thread that issued the read request is woken up and it begins to execute again. Just make sure everyone's clear on the difference between a process and a thread. A process is basically has its own address space, it has its own resources in terms of data and files, file handles, it has its own stack space, register copies, etc., code space. And it has a single thread of execution by default. When we introduce threads into a process, we share the data and files and code that's in that process, but we have different threads of execution which all have their own copies of the registers and have their own stack space. So each of these is effectively an independent unit of execution within the process that can see the global data available within the process and the resources such as files. So threads are much more efficient and lightweight compared to multiple processors performing concurrent behavior, because they share the same address space, and context switching between threads and communication between threads within the same process space is much faster. So when we introduce concurrency into a system, things become, as this slide says, fun. Concurrency introduces different sets of problems than we get in sequential programs. We have to deal with things called race conditions and things called deadlocks. And these are caused by non-determinism of the order of which things execute and the different interleavings of execution orders that can occur when we have multiple threads or multiple processes in our system. So let's look at these. First problem occurs when you have shared variables. We have two threads that want to make a change to exactly the same variable at exactly the same time. So here you can see thread number 1 wants to add 6 to a value of x, and thread number 2 wants to add 1. So what's the result of this? Remember that to change a value in memory, we need to read that value from memory into a register, execute the numeric instruction to change its value, and then write the value back to memory. So this addition is not what's known as an atomic operation. It's not a single operation, it's actually 3 different ones. So we could have this order where thread 1 starts, it reads X into a register on the CPU, it adds 6 and it writes the value back. And then as soon as that occurs, thread 2 reads the new value of X into a register, does its increment and writes the value back. And that of course is fine. That order of execution, that interleaving of execution is fine. What about this one though, where we read X into a register in thread 1 and we add 6 to it, but before we write it back, thread 1 gets descheduled and thread 2 gets scheduled. It reads the value of X from memory into a register, adds 1 to it, and then writes it back. It's then finished its work, it gets descheduled, and at some stage in the future, thread 1 is rescheduled and it writes its result back to memory. It's already added 6, it just needs to write it back. So what's the result of that one? Well, it's not good, because this means that thread 1 stomps over the incremented value of thread 2. We have what's known as a race condition. Because of the different order of these threads' execution, we get different results, or potentially get different results every time we run the program. So same program, different results, not good, not easy to debug. It really does depend on how your program is scheduled by the CPU. And it schedules it by interleaving the order of execution of threads, and different interleavings, different orders of execution can potentially produce different outcomes. And these things are extremely hard to debug because they're not easily reproducible, because the CPU controls the order of events of execution, not you. So when they occur in production systems and you can't reproduce an error that someone's seeing, it's not good. So the root cause of this is non-determinism. Sequential programs are completely deterministic in their behavior. You can read the code and know exactly what order it's going to execute in. But parallel programs, concurrent programs are not, because the multiple threads can have different orders of execution depending on what they're doing, what the CPU is doing. So this is what's known as non-deterministic. We can't determine the order in advance. There's two kinds of non-determinism. Observable non-determinism is bad. A program may give you different results in terms of race conditions occurring. What we want is non-observable non-determinism. Whatever order the threads execute in, we always get the same results. That's good. So non-observable determinism, let's have a look at this. Thread 1 assigns 2 to A and then adds 6 to A and stores it in B. Thread 2 assigns 9 to X and then makes a calculation on Y by subtracting 3 from X. These are good because they don't share anything, and whatever the order the scheduler runs these instructions in, we will always get the same result. So if we have no shared variables, then life is good. We always get non-observable determinism. If we don't, we have to think about race conditions. And to eliminate race conditions, we use something called locks. Locks are used to basically place a boundary around shared variables, so they can only be accessed by a thread which has acquired the lock before it changes the shared variable. So basically this provides a gate. A thread must come in through the gate, it shuts the gate behind it, it does its thing, it then opens the gate and leaves, and another thread can then come in through the gate. And this ensures non-observable non-determinism. These locks are often known as semaphores. There's different names for them, but they're essentially locks and that can be used to solve race conditions. So they essentially serialize access to shared variables. Every thread grabs the lock before it accesses the shared variable, it makes its changes and releases the lock. As soon as the lock is released, any thread which is waiting for the lock can then be scheduled to make its change to the shared variable. Which thread proceeds next, say there's 10 threads waiting on that particular lock, is typically non-deterministic. The scheduler makes that decision. There are sometimes prioritized mechanisms that you can introduce depending on the language and system, but typically it's determined by the scheduler. And so your program should take into account that behavior. In Java, the easiest way to do this is to use synchronized methods, as this example shows. Basically, you just add the synchronized keyword to a method, and this places a lock around the whole method so that it can only be executed by a single thread at a time. This is typically known as a critical section. As the slide says, it's not possible for two invocations of any synchronized methods on the same object to interleave. This is really simple to do. You don't have to explicitly grab the lock and release the lock in your code. That's done for you by the Java runtime. As soon as a method enters a thread enters the method, a lock is acquired and it's released automatically. You can't forget to release the lock when you exit the method. So that's a really simple mechanism to use. What critical sections do is they enable us to define atomic operations, and this is something that will become much more important as we talk about databases, but let's just make sure we understand the definition of atomicity. Operations A and B are atomic with respect to each other if, from the perspective of a thread executing operation A, when another thread B executes, either all of B has executed or none of it has. So we're basically saying that these two operations must fully execute or not execute at all when they share the same state. And so by introducing locks, we are making operations on shared variables atomic. So think about sharing a structure such as a linked list. When we try and change the size of the list by adding a new element, we read the size variable, we add a new element to the end of the list, and then we increment and write back the size variable because it's changed. Now here we're making changes to two things. We're making changes to the list structure and also the size. So these two operations must be atomic with respect to other threads. Otherwise, if you add something to the end of the list, but somebody else comes in and changes the size, decrements the size perhaps, before you've completed your operation and increased the size, then you're going to get some sort of weird, inconsistent result due to your race condition. So note that concurrent access to Java util collection libraries are not thread safe. So if you do use these in threaded programs, you have to introduce your own thread safety. Deadlock's another problem we get when we have concurrency. This occurs when two threads are sharing access to two shared variables via locks. Thread 1 takes a lock A and thread 2 takes lock B. Then they both do their thing, but during doing their thing, thread 1 blocks on B. It wants to make a change to the shared variable that's guarded by B. And at some stage later, thread 2 blocks on lock A because it wants to make a change to the shared variable blocked by lock A, controlled by lock A, sorry. Now note what's happened here. Neither thread can proceed because thread 1 holds lock A and is waiting for lock B, and thread 2 holds lock B and is waiting for lock A. Neither of them can proceed because they're waiting for each other. So what we have here is a deadlock or a deadly embrace. And this violates the liveness property of a system. And liveness basically means that something good eventually happens. The only way something good can happen here is if one of the threads releases its lock. So sometimes in systems, in threaded libraries, you can say I will wait on a lock for a certain time period. And if that time period expires, I will then relinquish the lock and maybe try again, come back and try again. Locks are of course bad because they cause your system to stop. And this is why concurrency is hard. If you have too few ordering constraints, you don't lock enough of your shared variables, you get race conditions. But if you lock things in slightly random or uncontrolled ways, you introduce deadlocks. So this makes testing of concurrent systems really, really hard, because there's essentially an infinite number of interleavings and you can't test them all. So that's just the summary of the problems that you will see in concurrent systems, but it's a core part of building a scalable distributed system. So in the rest of this module, you'll be doing reading from the Java Concurrency in Practice book and doing some exercises using Java's concurrency mechanisms. Have fun.